Hi everyone, I'm Jithin from Microsoft. So at Microsoft, my team and I, we design and build the backend network for AI clusters, develop communication libraries with a focus of exposing the hardware features to the applications, and also look at problems at scale, right? So today we are going to discuss some of the scaling challenges for scaling beyond, right? And also some of the key insights from our experiences so far, right? So I'd like to get started with some of the scaling journey and breakthrough Azure HPC AI breakthroughs, right, over the years. So like many of you here, right, we also started with a heavy focus on the HPC side of things. By HPC, I meant the traditional MPI or scientific workloads. So back in the days, we hit many breakthroughs, right, the 20K or 80K MPI job. And then later, with the Azure NDV4 and NDV5, which is the A100 and H100 SKUs, things really took off for AI, right? So we made into several of the top 500 lists and also MLPerf. And in last year, for the top 500, we made number one in the cloud with a rank of 3 overall. And also number 1 in cloud for MLPerf and rank 2 overall, right? And I'm proud to share that I led the team for the top 500 submission and also led the team for the networking side of things for the MLPerf submission. And it's amazing that we are in a really interesting time frame where scale is really exciting, right? So back in the days when I was a grad student, right? So when I see a paper of say 1K or 2K GPUs, I was like, oh wow, they got a big cluster. And now we are in a period where CEOs actually post on about multiple hundreds of thousands of GPUs, right? So it's really amazing. And it doesn't stop there, right? So the AI market is actually really pushing the scale beyond, right? So new markets are evolving, right? The data is actually getting diverse and large. And as a result, the models are becoming complex, and all of these actually push the scale beyond, right? And we all know the race is on, right? I mean, who finishes the training first, and then with the accuracy and performance details, right? So in this talk, I would like to start with some of the challenges in scaling beyond. And I would like to start in a logical manner, right? So starting with designing and building the cluster with the topology and the routing designs. I also want to talk about some of the challenges in validating the clusters, right? And then communication library, and also when you build the cluster, you have to run the training workload for periods of time, right? Maybe months or time, right? And then how reliably you can run. I also want to set the scope that, so I'm from the AI platform side of the teams at Microsoft. So a lot of the things here are about the networking and also the communication library, not a lot on the model optimizations or the parameter tuning, those kind of things, right? So yeah, let's get started with some of the challenges, right? So starting with network topology, right? So, I mean, we all know that the scale demand is actually pushing the switch radix. It's not about you cannot build a cluster with the switch radix, but I mean, it's actually about what's the oversubscription, right? Or how many number of layers that you're building, and how is actually impacting your workload, right? Is it actually good for your workload? You can also think about different topology options, right? Rail optimized, right? And also depending, you can ask the question of, do you have to merge the rails, or you can keep in a rail-only topology, right? You can also look at multi-plane, where a NIC is actually split into multiple planes. And you can also think about mixing these together, right? I mean, multi-rail or multi-plane, and then how do you do this together? And also, I mean, many of us are looking into the multi-pod or AI zones, right? In a different term. So do you want to do a single pod where every node has without oversubscription, or you want to do multiple pods, right? So that's another thing. And the key takeaway is that, you're building this network. How fungible is it for your workload, right? So I'll come to the insights later, but going forward, right? I mean, scaling beyond and validating the clusters. We all know these clusters are actually not built in a single day. it actually takes multiple weeks or even months, right? And you cannot keep your cluster idle. Right, you have to use it for training, and at the same time, new clusters are coming, right? So how efficiently can you validate the clusters, right? I mean, sometimes you cannot logically even divide also. So you'll need efficient benchmarks or validation frameworks. You can like specifically target the layers of the network and make sure things are all good, right? We also need like your benchmarks to be targeting particular links also, right? Sometimes the links can be of critical importance, right? And routing, right? Sometimes we take it for granted, right? I mean, you are building a network for a well-known topology, right? And then you expect the routing things will work well, even at scale, right? So here I've shown like 3 different data from during our initial cluster bring up, right? First one is about like multiple traffic pattern. One is an on-off or a continuous flow, right? What we observed is that between 2 generations, it took some time for the generation 2 to like hit to the peak bandwidth, right? Very interesting, right? And then another one is about like multiple flows, right? I mean, these are all micro benchmarks that are mimicking the actual training pattern, right? So in this case, we noticed that the first flow was actually taking much longer to hit the peak bandwidth. And this again happened at scale, right? Not point to point. And the third one, again, like very interesting, right? So you have multiple pairs of nodes talking between each other, and you over-provision the number of paths between them. So interestingly, like when there are like more than the number of communicating pairs, number of paths available, right? Your performance is actually low. For each of the pairs, you are actually hitting lower than the theoretical peak number, right? And as you reduce the number of links, then you are actually able to peak, right? So these are some of the things, key things that you need to like really look into and ensure things are working well, right? And these are not open issues. We worked with the networking partners and to get to solve it, right? Again, communication library. I mean, I think this is not a surprise, right, for the folks here. Many of the popular communication libraries are tuned specifically for a particular hardware and a particular topology, right? So there's enough scheme there or enough room for improvement in this case, right? The charts that I'm showing here are simple examples of like when you tune like say maybe QP tuning or protocol or algorithm tuning, right? For the targeted message sizes that are super important for the training job. I mean, we are able to like lower the latency, right? And thereby increasing the bandwidth, right? Another key thing here is that we always have to maximize the power across multiple regions, right? And what it entails is that your communication library should be able to like talk between regions. So you cannot rely on RTT-based communication algorithms for that, right? So you need to come up with different things. So that's another key takeaway from this slide. Again, reliability, right? So we looked deeply on like what are some of the factors that are impacting the training downtime, right? So link flaps is, again, one of the main or common one. So we again like split this into like say server to switch and switch to switch, right? So in the left one we have the server to switch, and we could see that like when the link flap duration is actually smaller than a particular threshold, again like tuning in together with nickel library, right? We can actually able to sustain the link down and continue with the job with a hit on the performance. On the other side, like smart NIC based designs can overcome these limitations, right? You can still hit the training job is actually able to get sustained performance without, even when the link flaps happen. So go to the next one. So yeah, let me jump into the key insights and solutions here, right? So we'd like to go into details of like the topology designs how we think about routing with these changes in the topologies. I also want to talk about the validation frameworks and COM library and the reliability. Right? So again, these are some of the different topologies that we are looking at. Again, we consider in two different classes of topology, right? One specifically targeted for public clusters, where you have to support a variety of different workloads, right? So what we are focusing these days, or till now, is actually a rail-optimized, non-oversubscribed cluster, right? Cluster design, where any node can talk to anybody else in the cluster without any performance impact, right? So the second graph indeed shown there, it's actually a bandwidth distribution of all the pairs of nodes talking in a cluster, right? So we can see a single band, right? So the goodness here is that you can enable all the different types of communication, right? So you don't have to, focus only on, say, all reduce or like reduce scatter. Like you can support all the different models, right? But on the other hand, for dedicated AI clusters, right? You have the opportunity to fine-tune or design it based on the workload characteristics. So you look at multiple different approaches here. So one of the main common themes in the AI field is the multi-pod based architecture. So within a pod, you can have zero oversubscription, and then anybody can talk between each other at full speed. But you can handle some level of oversubscription when it goes to between the pods. We also look at rail-only topology, right? So that means that you are enabling communication only within that rail. So this actually works very well for many of the collectives, right? And you can actually save a lot of money, right? This translates to a lot of cost savings, right? So you are taking the top layer of switches out. You can also, when you design these different topologies, like you can handle oversubscription, so you have a lot of flexibility in designing these clusters differently. And when it comes to routing, right, we are looking at multiple approaches, simple NIC and smart switch, or smart NIC and simple switch. And lately, we are focusing on a different idea, right? A smart NIC, simple switch, and a smart CCL. The key idea is that the CCL, or the communication library, can have a say on the routing configuration, right? And again, you can do in two different ways. One, the NIC is actually in charge of things, right? Selecting the best routing schemes, etc. But you can also get the hints from the communication library to the network. So the idea is that there could be some snooping agent or workloads or benchmarks there, and it can give a feedback to the control agent, and the control agent translates them to the communication library. So I've given a link to one of our papers here. So we are looking at derivatives of those ideas, right? So and making into production. And when it comes to reliability, right? So again, in this case, I'm showing a slide, the experimentation result, where again, multiple pairs of nodes communicating, right? And then you take down the links one by one. The key insight is that, the key result that we are actually looking for is that, you should see a proportional performance drop, but at the same time, the job should not fail, right? So we are actually able to hit that. But some other things, some other metrics also are important here, right? The time it takes for the CCL to react to those events, and how long the CCL will take to hit to the peak bandwidth, right? So that's an important metric here, right? The switch-based designs or the smart switch-based designs can handle this well, but the NIC-based or the feedback for the NIC, right, or the feedback from the communication library, those kind of designs can handle this even more gracefully. One of the other things we are mainly focusing these days is about the layers of links or the specific links that we need to focus. So we saw in the previous slide that the server to switch, those links are the most impactful one. But at the same time, how do we target those links, right? When you only have one node, right? You can always do a pairwise benchmark and get that. But again, that translates to some loss or capacity, or you will have to have multiple nodes to target that, right? So we are working with our networking partners to come up with intelligent tools to do that, right? And even before we plug it into the full fabric, right? So can we ensure that? And when it comes to frameworks for validating clusters, so we have our answer here is Superbench, and also our in-house benchmarking framework called IBPulse. So Superbench, again, I have put a link to the paper here. So the idea is that for the nodes, the Superbench monitors the behavior based on the results, right? And then based on those, right, it can model and come up with the different set of benchmarks that needs to be run on those nodes. And based on those results, you can actually classify this as actually a good node or bad node, and then take it out or run targeted benchmarks, right? So that's the main idea here. And again, this is customizable, right? So you can expand it to any node type or architecture type. And again, when it comes to the network, right? So again, part of the Superbench, and also there are additional benchmarks that we are in-house benchmarks, where we can target specific areas of the network or areas below a particular level of topology, right? And then you can and the benchmark tool will output a list of, say, good nodes or bad nodes, or bad links, or even NICs, right? So you can have estimate of
what's the expected bandwidth for this benchmark that I should see on a particular link, and then if it's less than a particular threshold, yeah, you can always list as bad links, etc. Right? So reducing the time for while bringing up the cluster, right? So that's the main goal that we are trying to achieve here. And again, communication library, right? So we have multiple directions that we are doing here. So Tutel is one of the public paper here. So here we are approaching hierarchical algorithms, right? So mainly targeting MOE or MOE models, right? So basically, rather than doing a linear all-to-all, right? So you can actually do 2D hierarchical, you shuffle the data over NV links, so that later when you do the network communication, right? So you actually gather the data together and then send it in one shot. The advantage is that you get better network utilization, and you actually are coalescing the data, so you get better performance also, right? Rather than spraying smaller packets across the network, right? And MSQL is another important one for us, right? So where you have really tuned set of configurations for different clusters. For example, you could say, I'm running on Azure NDV4, and this particular scale and this message size, give me the best tuning for that, right? So that's MSQL, and you can also write your HTL-based collective algorithms and then use that for your training, right? We are also, again, as we discussed before, right? We are also looking at tuning side of things, right? Like QP tuning or algorithm or protocol tuning, right? And again, to connect these two together, right? So earlier we talked about rail-only architecture, right? But the Tutel kind of algorithms or similar algorithms we could use to still keep the communication within the rail, but still translating that to a lot of cost savings, right? Because you don't need the top layer of switches. This may not work for all workloads, but at least for some targeted workloads, this can actually prove to be better, right? Another thing is non-RTT based algorithms. Right, so you always, when we are scaling out, we have the need to communicate between regions of clusters, right? The RTT-based algorithms will not work. So we are investing on how you can efficiently transfer without having to have an ACK back, right? So yeah, that's a quick overview. So yeah, we went over some of the scaling efficiency and scaling breakthroughs for HPC AI. We also reviewed some of the key challenges and insights on how we can address those. And at the same time, looking forward, right? I think that's the key, right? So we are seeing shifts in the network topologies, right? I mean, regularly we saw, right? I mean, at the same time, we saw like multi-plane and or multi-rail or combining together, right? So those new strategies. And another main thing is that the need for fine-grained routing, that's becoming more and more. That's an important area that we are looking into, right? And CCL, or communication library, playing an important role in the routing, right? Routing designs. So yeah, that's basically it. Thanks, everyone. Thanks for your time.